NASA has confirmed that Voyager, after nearly 4 decades of mission, it became the first human-made object to enter interstellar space, reaching a distance of 18.5 billion kilometers from Earth. Contrary to all expectations of durability, the probe remains operational thanks to the careful management of its plutonium power source, which has allowed its lifespan to be extended far beyond what was originally planned. However, the technical data recently sent back is puzzling the scientific community. Although the instruments are functioning perfectly, the readings of the interstellar environment do not correspond to known theoretical models. What Voyager is now describing is a space scenario that science did not predict, transforming an old planetary reconnaissance mission into a journey into the absolute unknown. But before we begin, don't forget to like and subscribe to our channel. Even operating with minimal power, after shutting down cameras and secondary instruments to preserve its survival, Voyager 1 spacecraft remains in communication with Earth. This engineering feat allows the probe to continue transmitting essential data, defying its projected lifespan and maintaining an open channel with humanity from the depths of interstellar space. Although the signal travel time is currently over 22 hours and recent discoveries focus on refining existing scientific models, the spacecraft's persistence in sending technical information demonstrates the effectiveness of the energy conservation protocols adopted by NASA over decades. Decade after decade, the signals kept coming. Weak, delayed, but consistent. Each transmission carried data from farther away than any direct measurement ever made by humanity. A Voyager. It wasn't just leaving the solar system. It was entering a region where no spacecraft had ever been before. That alone would be enough to make it one of the most important missions in history. But the farther she traveled, the more her role began to change. It was no longer just about exploring planets. She was approaching a limit. For years, scientists have defined the outer edge of the solar system based on the reach of the sun's influence. The solar wind, a stream of charged particles moving outward from the sun, creates a kind of bubble around the solar system known as the heliosphere. Within this bubble, the sun's magnetic field dominates. Outside of it, the environment is shaped by the interstellar medium, the matter and energy that exist between the stars. The boundary between these two regions is called the heliopause, and Voyager 1 was heading directly towards her. This transition was not expected to be gradual or ambiguous. The models were clear. As the spacecraft approached the heliopause E, the solar wind would weaken, the density of interstellar particles would increase, and, most importantly, the direction of the magnetic field should change, shifting from an orientation dominated by the sun to one aligned with the galaxy. It was supposed to be obvious, a clean separation, a measurable passage from one region of space to another. Voyager. It carried the necessary instruments to detect this transition. Even in its reduced state, it could still measure magnetic fields, plasma waves, and charged particles. In practice, it was a sensor steadily moving toward a line that scientists believed they understood. And as it got closer, the data began to change. The solar particles decreased, cosmic radiation increased, plasma density changed in ways that matched the predictions. Everything pointed to a single conclusion. A Voyager 1 was nearing its limit. But there was a problem. The closer it got to that boundary, the more crucial a single measurement became: the direction of the magnetic field. Because that was the signal that could confirm, without ambiguity, that the spacecraft had left the sun's influence behind. It was the detail that would separate theory from observation, expectation from reality. And when Voyager 1 finally reached this point, this signal did not change in the expected way. The frontier that hasn't changed. In August 2012, Voyager 1 reached the moment scientists had been waiting for, the instant it crossed the heliopause, the outer limit of the sun's influence. Based on decades of models, this transition should have been one of the clearest events ever recorded in space exploration. The predictions were specific. As Voyager approached the boundary, the solar wind would decrease dramatically. At the same time, cosmic rays coming from outside the solar system would increase. And most importantly, the magnetic field should change direction, ceasing to be aligned with the sun and becoming controlled by the galaxy. 3 signs: clear, measurable, and consistent. When the data started coming in, 2 of these signals appeared exactly as expected. The solar wind weakened, cosmic radiation increased. Everything indicated that Voyager had reached the edge of the heliosphere. But the 3rd signal, the most important one, didn't change. The magnetic field remained practically in the same direction. This shouldn't have happened. entering interstellar space should be like entering a completely different environment. The magnetic field on the other side should have a different orientation, shaped by forces beyond the solar system. Instead, it was as if Voyager had crossed the boundary and found the same structure continuing on, like walking through a door and seeing the same environment. Initially, scientists hesitated. The data was clear, but the interpretation was not. Had Voyager truly crossed the heliopause? Or was it still within a region influenced by the Sun in ways that were not fully understood? The measurements offered no simple answer. They created a contradiction. Because if Voyager were still inside the heliosphere, the increase in cosmic radiation wouldn't make sense. But if it had left, the unchanged magnetic field wouldn't make sense either. The boundary was supposed to resolve this uncertainty. Instead, it created it. Subsequent analyses confirmed that the plasma density had increased significantly, exactly as scientists expected from interstellar space. This reinforced the idea that Voyager had indeed entered a new region. But the magnetic field continued to behave as if it were still connected to the Sun. This left only one possibility. The boundary was not as scientists had imagined. Instead of being a clear line separating two distinct regions, the heliopause appeared to be more complex, a transition zone where properties of both environments overlapped. The Sun's magnetic influence didn't simply stop. It extended outward, interacting with the interstellar medium in ways that blurred the distinction between inside and outside. This changed the meaning of the journey. Voyager didn't move from one clearly defined region to another. It entered a space where the rules were less clear, a space where the influence of the Sun and that of the galaxy existed simultaneously. And this raised a deeper question. Because if the boundary itself wasn't well defined, then each measurement taken within it became more difficult to interpret. The data no longer described two separate systems. They were describing an interaction between them. And interactions are harder to model, harder to predict, and harder to fully understand. Which meant that the anomaly wasn't just the magnetic field. That was the assumption behind it. Because everything about that crossing had been based on the idea that the edge of the solar system could be clearly defined. But the Voyager data suggested otherwise. They suggested that the edge wasn't a line, it was a region. And the moment scientists accepted that, a new question replaced the old one. It wasn't whether Voyager had crossed the border, but what kind of border it had actually crossed. The signal didn't match. After the 2012 crossing, Voyager won. It did not stop providing data. She continued advancing, deeper into what was now considered interstellar space, and as the years passed, her measurements were expected to stabilize. Once beyond the heliopause, the environment should become more uniform, less influenced by the Sun and more by the broader structure of the galaxy. That was the expectation. But the data didn't stabilize as it should have. One of the main instruments still active on Voyager, one of its features was its plasma wave system, which detects oscillations in charged particles. These plasma waves are important because they reveal the density and behavior of the medium through which the spacecraft is traveling. In interstellar space, scientists expected relatively stable readings, with occasional perturbations caused by distant cosmic events, such as shock waves from supernovas. And initially, that's what the data seemed to show. Voyager detected bursts of plasma waves that allowed scientists to measure the density of the interstellar medium with surprising precision. These readings confirmed that the spacecraft had indeed entered a region denser than the heliosphere, reinforcing the conclusion that it had crossed into interstellar space. But over time, the pattern of these signals began to change in ways that didn't fully match the models. Some of the variations were linked to known events, such as shock waves propagating through space from distant stellar explosions. But others emerged without a clear source. The density increased, then stabilized, and then changed again. These changes weren't extreme, but they were consistent enough to raise questions, because interstellar space, at least in theory, shouldn't behave like a highly dynamic system on this scale. It is vast, diffuse, and relatively uniform when compared to planetary environments. Small variations are expected, but not persistent fluctuations without clear causes. Voyager was detecting structure. At the same time, its cosmic ray instruments were recording changes in the intensity of high-energy particles. These particles, originating outside the solar system, should have followed predictable patterns once the protective effect of the heliosphere was removed. But even these readings showed variations that did not align perfectly with what was expected. What made this even more significant was the way these different systems began to overlap. Changes in plasma density, fluctuations in cosmic rays, and the behavior of the magnetic field were all showing small inconsistencies at the same time. The environment Voyager had entered was not as simple as the models suggested. It had structure, and that brought the focus back to the frontier. If the heliopause wasn't a clean separation, and if the region beyond it wasn't entirely uniform, then Voyager wasn't moving from one stable system to another. It was traversing layers, which meant that the fluctuations in its data weren't necessarily errors or anomalies. These could be measurements of something more complex than expected, something that hadn't been fully considered in the original models. And this changed the interpretation again, because now the question wasn't just about the boundary itself, but about the nature of space beyond it, the forces we don't take into account. By this point, the pattern was already difficult to ignore. Voyager 1 had crossed the heliopause, but the transition was not clean, and the space beyond it was not uniform. The plasma density varied. The magnetic fields did not fully realign. The behavior of the particles overlapped between regions that should have been separated. Initially, this was treated as anomalies, but over time, a different interpretation began to emerge. The problem might not have been in the data, but in the model. For decades, the heliosphere was described as a kind of protective bubble around the solar system, formed by the pressure of the solar wind pushing against the interstellar medium. The boundary, the heliopause, was considered the point where these two forces balanced each other. But real-world environments are rarely that simple. When scientists began to re-examine the Voyager data in detail, they started to consider the possibility that the heliosphere is not a smooth, symmetrical structure. Instead, it may be distorted, stretched, and shaped by external forces in ways that had not been fully considered. One of the most important of these forces is the interstellar magnetic field. Unlike the Sun's magnetic field, which radiates outward, the interstellar field exists on a much larger scale, influenced by the movement of the galaxy itself. As the solar system moves through this medium, the interstellar magnetic field does not simply stop at the heliopause, it interacts with it. This interaction creates a phenomenon known as magnetic draping, where the lines of the interstellar magnetic field curve around the heliosphere instead of passing directly through it. Instead of a sharp boundary, a layered region forms where the solar and interstellar fields overlap and influence each other. This changes everything. Because if the magnetic field outside the heliopause is being curved and aligned along the surface of the heliosphere, then Voyager, upon crossing that boundary, would not immediately detect a new direction. It would detect continuity, which is exactly what the data showed. The magnetic field did not change abruptly because it shouldn't change. It was being shaped by the interaction between two systems at the same time. But this still doesn't explain the fluctuations, because draping alone would create a smoother transition, not the layered variations that Voyager detected. This led scientists to consider additional factors, including boundary turbulence. Instead of being stable, the heliopause may be in constant motion, with mixing regions where particles from the solar wind and the interstellar medium exchange energy. Think of it less as a wall and more as a current. This type of environment would naturally produce the variations that Voyager recorded. Plasma densities would fluctuate, particle distributions would change, and magnetic fields would appear consistent in some areas and slightly altered in others. The signals sent by Voyager take more than 20 hours to reach Earth. What scientists analyze is not real-time data. It is a belated snapshot of conditions that may have already changed by the time they are observed. This makes it even more difficult to reconstruct a stable picture of the environment. All of this points to a single conclusion. The region around the heliopause is not a boundary in the traditional sense. It is a zone of interaction, a place where forces overlap, compete, and continually reshape each other. And Voyager not only crossed it, it is still moving through it. This means that the fluctuations in your data are not merely traces of a transition. They may be ongoing measurements of a system that we don't yet fully understand. And this leads to a deeper implication. Because if the outer edge of our solar system is so complex, then the idea of a clear separation between inside and outside may simply not apply. And that changes how we think about where the solar system actually ends, where the solar system truly ends. At the moment when a point was crossed, which scientists call the heliopause, this should mark a clear milestone. But the data never fully supported this idea, because if the heliopause is not a defined boundary, if it is a region where solar and interstellar forces overlap, then the concept of an edge becomes more difficult to define. Voyager didn't just pass from one side to the other, It entered a zone where both environments still exist simultaneously. Inside the heliosphere, the Sun dominates. Outside of it, the galaxy dominates. Voyager data suggests that this distinction may not be absolute. Instead, the solar system may extend farther than we imagined, not as a defined structure, but as an influence that gradually diminishes. The Sun's magnetic field, its particles, and its energy do not simply stop at a straight line. They weaken, interact, and blend into their surroundings. This means there may not be a single point where the solar system ends, but rather a region where it gradually disappears. And this has real consequences for how we interpret Voyager's position. Because although it is technically in interstellar space, it still detects effects linked to the Sun. The alignment of the magnetic field, the behavior of the particles, and the plasma fluctuations suggest that the influence of the solar system has not yet completely disappeared. This also explains why Voyager's data doesn't fully match interstellar models. These models assume a cleaner environment, where local influences are minimal. But Voyager is measuring a space where these influences are still interacting, a space that is not completely one thing or the other. This means that each reading sent by Voyager is part of a larger transition, not a fixed state. Transitions are more difficult to interpret than stable systems. They contain overlapping signals, variable conditions, and interactions that do not stabilize into predictable patterns. That's exactly what Voyager has detected, and that leads to a more accurate way of understanding what Voyager actually did. She didn't reach the edge of the solar system. She reached the limit of how clearly we can define that edge, because if the border itself isn't fixed, then the idea of crossing it becomes less significant. Voyager didn't leave one known region for another. It entered something that is still being defined. If the solar system doesn't end where we thought, then what exactly have we been measuring all this time? What is Voyager really showing us? After everything that Voyager 1 observation noted, that the biggest change is not in the data itself, but in how that data is interpreted. For decades, space beyond the solar system was treated as something simple, a vast and almost empty region where particles move, magnetic fields extend over great distances, and changes happen slowly and predictably. The heliopause was supposed to mark the transition to this simplicity. The measurements sent by Voyager 1. They reveal that the transition between the solar system and interstellar space is far more complex and structured than scientific models predicted. Instead of a sharp, divisible boundary, the data describe a region of continuous interaction, where magnetic fields and particle densities dynamically overlap. This discovery does not indicate a flaw in physics, but rather a limitation of human theoretical simplifications that treated the cosmos as isolated zones with fixed rules. Thus, the probe did not find an anomaly, but rather the need to redefine our understanding of the scales and fundamental interactions of the universe, proving that, even after decades, we are still learning to accurately describe the environment beyond our system.